Get your favorite dishes delivered home. Order online.
Okay, hello everyone. Please type in your name so that I can understand that who are there. Okay, Jishnu, Shreya, Shreyas, Areman. Wait, Gaurav, I'll tell you. Sridhamya, Shris, Ramesh. Uh, which class you are in, Shris Ramesh? Okay. Anyways, uh, see, today we are going to discuss some basic concepts of general organic chemistry. Okay, this is only for school exam basics level. Basic level will do. Okay, I have already started this in 11th class HSR and PSHSR, but at Rajinagar I will start soon. Okay, so again, all these things we'll discuss in the class and we'll go into so detail to up to JEE advanced level. Okay, so today's class will just go through the basic concepts of this so that when we discuss this again into the class and we'll go to the advanced level concept, you can understand it properly. Okay, that is the purpose of this class we have. Okay, so actually there are few electronics effects. If I talk about chapter we are going to study today, that is general organic chemistry. Okay, now in this there are a few things that I will not discuss today, which usually I start from, right? But I will not discuss it today. We'll discuss this in the class when we take the physical class or offline class. Okay, so those for like, especially for Rajinagar guys, if you are, you just try to understand the concept we'll study. Okay, it's not like complete thing we are doing today. Okay, since many of you are not here today in this session. Okay, so for Rajinagar, I will discuss this thing again into the physical class also. So don't worry with that. Okay, so few things I am not discussing it here, right? That I will discuss in the class, but again the basic concepts that we have already done in chemical bonding of in chemical bonding, and that is resonance. So we'll start today's class, we'll start from the concept of resonance. Okay, once we have already done this particular concept in chemical bonding, what resonance is, and how do we draw the various resonating structures. Okay, okay, so the point is, this actually the part of GOC. If you remember, I told you this thing in the class when we were doing chemical bonding that we will discuss this again into GOC. Okay, so here we are going to discuss resonance again. So first of all, you see what is resonance. So the definition of this is what? It is the phenomenon. It is the phenomenon in which two or more molecules, in which two or more structures, two or more structures can be drawn for a given compound, for a given compound, but none of them, whatever structures we draw, but none of them represents the actual molecule, represents the actual molecule. Okay, the structure we draw here, all these structures, like I said, two or more structures, right? So all these structures are called resonating structures. Okay, so next line you write down, all these structures are known as resonating structures. Okay, resonating structure or canonical structure, we also call it as canonical structures. Okay, so from now onwards, these resonating structure will use RS to write down the resonating, because every time we have to write down this particular thing, resonating structures here and there. So we'll use RS as resonating structure. Okay. Like you see, examples, if I write down the structure of benzene, the structure is this. Okay. And we can also draw another structure as this. Okay. And these two are called resonating structure of benzene. If you look at this molecule looks like similar molecule, but they are not similar. Okay, they are different molecules, because if you do the numbering over here, 1, 2, 3, 4, 5, and 6. Here, if you do in the similar way, 1, 2, 3, 4, 5, and 6. Okay, so both these structure you see here, the double bond we have between 1 and 6 carbon atom. Here we have 1 and 2 carbon atom. Here you see 1 or 2 carbon atom, we have single bond. Right, so both these structures are different structures, right? And both these structures we call it as resonating structure or canonical structure. The actual structure of benzene is not this or this. These two are not, these two does not represent the actual structure of benzene. Then what is the actual structure of benzene we have? You must have seen the structure of benzene in the book. It is written like this, a circle in between. Okay, so this is what, this is the actual structure of benzene, or true structure of benzene. And this structure we call it as hybrid structure. Hybrid structure. Why hybrid structure? Because in any molecules where resonance is possible, this is nothing but, you see, one single molecule benzene we can represent in two different form, right? So this phenomenon is resonance, right? But none of these molecule represents the actual structure of benzene. So actual structure of benzene is this. Now what is this actual structure, or we also call it as hybrid structure? Hybrid structure means what? These two, see, this structure has certain properties. This structure also has certain properties. Okay, so the actual benzene, if you take, that will contain the properties of this structure also and this structure also. So when you combine these two molecules, you'll get a hybrid molecule. That hybrid molecule is a hybrid structure. Okay, so actually when you are able to draw a resonating structure of any compound, so all those resonating structures collectively or combine into the hybrid structure of that molecule, right? And none of these resonating structure represents the actual molecule. Actual molecule is the hybrid of all these resonating structure, right? Now if we talk about this benzene molecule here, you see, what is this circle that I put here in like on this molecule? What this circle means actually? You see here, in these two molecules, we have double bond between first and second, third and fourth, fifth and sixth carbon atom. Here we have second and third, fourth and fifth, first and sixth carbon atom. So actually, what we say that in the actual benzene molecule, this double bond is this pi electron which has this double bond, this pi electron delocalize over the entire molecule through resonance. Okay, now the point is here, if these two structure you compare, first and second carbon has double bond, first and second carbon has single bond. So if I ask you what is the bond length or bond order of C1 and C2 carbon in benzene molecule, right? Point here is what? If I ask you this question, what is the bond order of C1, C2 carbon in benzene molecule? Right, C1 and C2 carbon in benzene molecule, right? So from this structure, it will be 2. From this structure, it should be 1, right? But since the actual benzene molecule is this, with these two, we cannot give this answer because these are not the real structure. The real structure is this. And now, this actual molecule you have to consider for this answer. Now, in this, what happens? The bond order or number of bond between first and second carbon will be somewhere in between 1 and 2. It won't be 2 exactly, it won't be 1 exactly. It will be somewhere in between 1 and 2, right? So that's what the resonating resonance we have. Okay, the meaning of here is what? Here we have 3 pi bond, means 6 pi electron we have. Through resonance, what happens? This 6 pi electron delocalized over the entire molecule like this, and it continuously moves around this molecule like this. We have an electron cloud which continuously moves over this cyclic structure, and this movement of the electrons is nothing but resonance we have. Okay, so resonance is what? Resonance is nothing but is a phenomenon by which two or more structure can be drawn for a given compound. Now how this structure draws? By the movement of electrons, pi electrons. Okay, so basically this kind of resonating structure uh, gives a kind of stability also to the compound. We'll talk on this stability thing later on. Okay, but resonance is this only. Now when you draw this molecule, right, actual molecule is this pi electron is continuously moving over the entire molecule like this. Now the point is what? If the actual structure is this, then why we draw these two structures? Whenever you see any reactions, they must have drawn this structure or this structure, not this one. They never draw the actual structure of benzene while they represent the reaction of benzene. The reason behind this is what? In this structure, which is the actual structure of benzene, the electrons keeps on moving over the entire molecule. These are not static electrons, right? And to represent any reaction, we must require static electrons like this or this, right? So we use any of these molecule to represent the reaction of benzene. But actual molecule of benzene is this, which is due to resonance. Understood this? So these two are resonating structure or canonical structure. This is hybrid structure, or we also call it as resonance hybrid, or we also call it as resonance hybrid. Okay, the resonating structure also call it as resonance hybrid. Now, there are some condition of resonance. Okay, that condition you have to keep in mind, and if on that condition only the resonance is possible, otherwise it won't be possible. Okay, so next thing we'll see condition of resonance. There are some more example in this we'll see, but after this condition we'll see some more examples onto this. Okay, so first of all you write down condition of resonance. The first condition is it involves it involves all of you write down these conditions. It involves delocalization of pi electrons of pi electrons. All resonating structures, all resonating structures must follow octet rule. Second one, resonating structure, resonating structure which has more covalent bond, more covalent bond are more stable, are more stable. Third one, third one you write down. All resonating structure must be planar. Planarity is the necessary condition for any molecule to show resonance. Okay, if the molecules are not planar, resonating structure we cannot draw. Next one, delocalization of electrons takes place in parallel p orbital, right? And which is only possible when the molecule is planar. That's what it is. Fifth one, molecules must have conjugated system. What is conjugated system? We'll discuss now. Molecules must have conjugated system. Now, what all systems are said to be conjugated? First one, all these are examples of conjugated system. If you have carbon, C double bond, C single bond, carbon with positive charge. This is a conjugated system. The meaning of this is what? We should have a double bond, then a single bond, and then a positive charge or vacant p orbital. This is the meaning of this particular thing we have. We'll see the example of this also, then you will understand that what is the meaning of this. First of all, you write down this. This is one type of conjugated system. Another one, if you have C double bond C, single bond C and negative charge on it, conjugated system. If you have C double bond C, single bond C and lone pair on it, conjugated system. If you have double bond, single bond and double bond, conjugated system. We have positive charge, single bond and lone pair if you have, then conjugated system. Negative charge, single bond and vacant d orbital. Vacant d orbital, conjugated system. If you have double bond, single bond and free radical, conjugated system. Okay, so all these are examples of conjugated system. Okay, now on the basis of this, if I ask you some question here, like which of these are conjugated system, right? First example you see, if I write down this one, C double bond C, double bond C and double bond C. Is this a conjugated system? Double bond O with lone pair on it. Is this a conjugated system? C double bond C, single bond C and triple bond C. Is this a conjugated system or not? See, the first one we have here, if you compare this, it has a pi bond, right? Then we have sigma and then we have pi. We have one more pi here, but that is not our concern. Our concern is what? If you have pi sigma pi. So we have here pi sigma pi. So this is a conjugated system. Similarly, this one you see, we have a pi bond, then we have a sigma bond here, and then we have a lone pair, right? So pi sigma lone pair. Where is this? See here, pi sigma and lone pair. This is also a conjugated system. Now when you can consider this pi sigma and again we have pi here. So this is also a conjugated system. Okay. One note you write down here. sp3 hybridized carbon never takes part in resonance. Okay, sp3 hybridized carbon will never take part in resonance. Next one. Next, write down characteristics of resonance or resonating structure. Anything you can write. Characteristics of resonance or resonating structure. First of all resonating structures are imaginary. They are not real structures. All resonating structures are imaginary. Second one, all RS contributes to real structure or resonance hybrid. Contributes to real structure or resonance hybrid. Next one, write down. Among all structures, real hybrid or resonance hybrid, both are same thing. Real hybrid will have least energy and it is most stable. That is why the actual molecule exists in real hybrid form. Okay, most stable. What is this RS contributors? I will discuss this. Okay, first you write down all these properties. Real hybrid will use RH for this term, real hybrid. Okay, write down real hybrid with more number of RS is more stable. Means for one compound, if you can draw 3 resonating structure, and for other compound, if you can draw 5 resonating structure, then the compound with 5 resonating structure will be more stable. That's the meaning of this. Last point you write down into this. In some cases, equal contributors are present. Equal contributors are present. What is this contributor? I'll discuss just now. Just wait for some time. Contributors are present. Equal contributors are present. In this case, the stability is especially very high, even if the total number of RS is less. even if the total number of RS is less. I'll discuss this contributors part now. Okay. Now you see, if I draw one molecule, now we'll take the example here. Suppose the molecule we have now, and this one I have already discussed in chemical bonding, I will discuss now also. CO3 2 minus carbonate ion. Okay, so carbonate ion, if you draw the structure of this, the structure will be like this. You see, C double bond O, single bond O minus, and single bond O minus. This is the structure. Now, this structure, how we get this structure, that you can understand by Lewis structure of this. Okay, Lewis dot structure you can draw, you will get this. Now you see here, is this a conjugated system? You see, pi sigma negative charge. It is a conjugated system. Pi sigma negative charge means if it is a conjugated system, then we can draw the resonating structure of this. And how do we draw the resonating structure? For that, what happens? This negative charge comes over here onto this bond, and this pi bond goes onto this carbon atom. Okay, now if you're numbering this oxygen as 1, it is 2, it is 3, and 4, right? So when this electron pair comes over here, we'll get a double bond here, and this pi electron goes here, we'll get negative charge here. So the structure will be, now it is C carbon O negative, double bond O, single bond O minus. Another structure also we can draw, and that structure is this. This negative charge comes over here, because here also you see pi sigma negative charge, pi sigma negative charge. Negative charge electron comes over here, and this pi electron goes onto this oxygen, and the structure will be this. C single bond O minus, double bond O, single bond O minus. Now if you see the position of double bond in all these molecules, this is first oxygen, second, third, and fourth. First, second, third, and fourth. Right? First of all these structures are resonating structure. Okay, all these are resonating structure. Okay, and since these are resonating structure, so these are not real structure. One more thing I'll tell you here, all these resonating structures are separated by this double-headed arrow, right? Resonating structure of any molecule, if you draw, those resonating structure will be separated by this double-headed arrow. Why this double-headed arrow we are using? Because the meaning of this is what? This structure can be converted into this, and this also can be converted into this. Both way it can go, right? That's why we are using double-headed arrow. Anyway, so this is what the resonating structures we have. Just a second. Hello. Hello. Yes, speaking. Yeah, 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 yeah. Sorry, what? No, 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 it's fine. Fine. Okay, so these are resonating structures, and these are not real structures. Okay, so if I draw the real structure of the of this molecule carbonate ion, that is resonance hybrid or real hybrid. Okay, so that will be like this. You see, carbon, oxygen, and oxygen. So we'll draw like this: carbon, oxygen here, and here we have again oxygen. Right. Now you see here one thing, that in the first compound, this one, we have double bond between this and this carbon. If I numbering this first, let me write down the number here. 1, 2, 3, and 4. Right. So here we have double bond, and all these molecules we have single bond. Right. Between C2 and oxygen O3, we have single bond in the first, double bond in the second, and single bond in the last. Similarly, in this also, 2 and 4 also. So all these molecule, what we say, these won't have any double bond or single bond, but they have a bond which is in between double and single bond. And we draw this delocalization of electron like this, with this dotted line. And then here also we have the dotted line. Okay, means what, this pi bond is distributed uniformly over this oxygen atom. One more thing, if I ask you about the charge on oxygen atom, you see on the first oxygen there is no charge in the first structure, but in the last two structure we have negative charge, right? So this 2 negative, which is here, this 2 negative charge is equally distributed over this oxygen atom. So how many oxygen atom we have? We have 3 oxygen atom. So 2 charge distributed among 3 oxygen atom. So here in this resonance hybrid, the charge on each oxygen atom will be minus 2 by 3, minus 2 by 3, and minus 2 by 3. So this structure is the actual structure of carbonate ion. This is resonance hybrid or real structure. Now, this resonance hybrid is the will have the property which is given by all these resonating structure. Means few property will be contributing by this first structure, few property will be contributing by this second structure, and few will be contributing by this third structure. So all these resonating structures will contribute into the properties of resonance hybrid. Okay, see, the reason of the charge minus 2 by 3 is what? We have minus 2 total charge, right? But in all these structure, what happens? This pi electron is delocalizing over the entire molecule. You see here, first of all, in the first structure, we have double bond between first and second. Second structure, we have double bond between second and third. And third one, second and fourth. So this means what? All these bond will have double bond in each of these structure, right? It means what, that this pi bond is distributing over the entire molecule. It is between 1 and 2 also, 2 and 3 also, and 3 and 4 and 2 and 4 also, right? So the point is, this charge, which is minus 2 charge, is distributed equally over the 3 oxygen atom, right? So total charge is minus 2 distributed among 3 oxygen atom. So each oxygen atom will have charge minus 2 by 3. Okay, each oxygen atom will have charge minus 2 by 3. Now the point is, this structure is the real structure, and this structure will have property given by all these resonating structure, right? Means suppose this has, suppose 10 properties I can write for this one. So it is possible that few properties will be given by this molecule, few will be given by this molecule, few will be given by this molecule. So actually this structure the is the combined structure of all these resonating structure, right? That's why the properties of resonance hybrid is given by resonance is given by its resonating structure only, right? So since these resonating structure contributes into the property of resonance hybrid, so we also call it as uh, contributors. All these resonating structures also call it as contributors. Now in this it is possible that one resonating structure will contribute maximum, other contributes minimum, right? Or another possibility is what all resonating structures contribute equally, right? So when all the resonating structures, write down this point, when all resonating structures contributes equally to resonance hybrid, resonance hybrid, then they called as equal contributors. Like the example I have taken just now, this is the case of equal contributors. All these resonating structures contributes equally. Whenever you have uniform distribution of pi electrons, they will have equal contributors. Okay. If one resonating structures contributes more than the other, then it is known as major contributors, right? If they contributes equally, then equal contributors. If one of the resonating structure contributes more than the other structures, then that particular structure we call it as major contributors, and all other one are the minor contributors. Okay. If one RS contributes more than the other RS, then it is major contributors, and others are minor contributors. Write down this. And others are minor contributors. Okay. Now we'll see again some example here. Next example you see, we have to draw the resonating structure of it. CH2 double bond CH, single bond CH2 plus. Is this a conjugated system? Tell me, yes or no? Is this a conjugated system? Is this a conjugated system? Yes, this is a conjugated system because we have pi sigma and positive charge. Okay, pi sigma and positive charge. Now when you look at this molecule, I'll just draw the exact structure of this first, because it's the first example here we are discussing. So here you see this three carbon are bonded like this: carbon, carbon and carbon, and this carbon has two hydrogen, this carbon has two hydrogen, and there is a pi bond which forms by the lateral overlap of this p orbital of these two carbon, right? This is the lateral overlap we have, and pi bond forms. And here we have one p orbital which is vacant. That's why it is this carbon has positive charge on it. Positive charge means what? It has loose is electron, right? So that's why this orbital is vacant now. There is no electron present into this orbital, and that's why when this electron pair jumps over here, it can accept this electron and will have a pi bond over here. So here you see when you draw the resonating structure of this, that will be this bond pair of electrons jumps over here, right? And we get the resonating structure. And since these, I'm going to draw the resonating structure here. So I have given this arrow, double-headed arrow, to separate these two resonating structure. Now, the resonating structure of this will be, you see this carbon, carbon, single bond, carbon, right? This has two hydrogen like this carbon has two hydrogen. Everything will be as it is. Only change will be what? This bond pair will shift here between these two carbon atoms. That is the only change. Every other thing will be same. Now you see here, since this carbon which has one electron here and one electron here, and both this one electron jump over here, and now this bond pair of electron is shared between these two carbon atoms, right? This one and these two carbon atom. So obviously one electron this carbon has loosed, right? This carbon loses its electron. So that's why here we have the positive charge on this carbon atom, right? And the pi bond shifted over here, right? So these two are the resonating structure of this molecule. 2RS we have, two resonating structure possible. But again, in the exam, you don't have to draw this orbital thing, right? This orbital, you don't have to draw. Then what do we write here? Suppose the compound is this, which is given in this. Then we have a double-headed arrow. This pi electron shifted over here. And then we'll write CH2, single bond, CH, double bond, CH2. And since this electron pair, one of this carbon shifted over here, right? So this carbon loses its electron. So here we have the positive charge. And this carbon already has one positive charge, taken one extra electron. So this electron will neutralize this positive charge. We don't have any charge onto this carbon atom, right? One more thing you must keep in mind, number of charges present in one resonating structure will always be same on all other resonating structures. Like you see, these two are RS of each other. This contains one positive charge, so another RS must contains one positive charge, right? That is the thing we have. Understood? So this is the orbital diagram I have drawn here to make you understand. But this you don't have to draw in the exam. Just you do like this, shifting, and you'll get that. So if I ask you how many RS possible for this, total RS resonating structure is 2, right? This also they ask sometimes in the exam. For this molecule, how many RS resonating structure we can draw, right? Another one you see, if one more example we'll see here. Oh, before that, we'll see one more thing here. Just you'll now, since I said that these two are resonating structure, these two are not the actual molecule. So if I ask you to draw the actual molecule, how do you draw? So first of all, you just write down all those sigma bonds, and that will be CH2, single bond CH, single bond CH2. Now this you see this pi electron is shifting, is distributed among these carbon, right? 3 carbon. If it is 1, 2 and 3, this is also 1, 2 and 3. So pi electron is between 1 and 2 and here between 2 and 3. So here we have the partial double bond characteristics. It is not the actual double bond we have here. In the actual structure, these two carbon and these two carbon will have partial double bond characteristics, and that will denote by this dotted line. This dotted line means that this has partial double bond character. This bond is not exactly equals to carbon-carbon single bond, not exactly equals to carbon-carbon double bond. It is somewhere in between single and double bond. Now here you see the positive charge in the first structure has at third carbon, and here it is at first carbon. So these two carbon will have slight positive charge. So del plus, del plus. This is the actual structure or resonance hybrid. Resonance hybrid. So when you take this molecule, actually the structure of the molecule will be this. This we write to for our own convention, for our own ease, like to represent the reaction and all. Okay. Now, if I give you one more molecule here, CH2, double bond CH, single bond CH, double bond CH, single bond CH2, positive charge. Is this a conjugated system? Is this a conjugated system? Tell me. This molecule is a conjugated system or not? You see the rules actually. What is the condition we have for resonating structure? It must have conjugated system, right? So you see here it is pi sigma and positive charge. See here this one, it is pi sigma and positive charge. So this is a conjugated system. So you can draw the resonating structure of this, since the resonance is possible into this. Now how do we draw the resonating structure? This pi electron jumps over here, right? And we get what every other thing will be same. CH2, double bond CH, single bond CH, single bond CH, double bond CH2. Now you see here, this CH2 takes this electron pair neutral, and this carbon loses its electron, right? So this carbon, the third carbon, will have the positive charge. So here we'll have the positive charge. This is the one resonating structure we have. Now in this, the another resonating structure is also possible, because you see again it is pi sigma and pi. If this bond here also pi sigma and positive charge we have. If this bond comes over here, we'll get this structure only, first structure only, right? So this is first structure, this is second structure. Now when this pi bond comes over here, we can draw the third structure here, which is nothing but CH2, CH, double bond CH, single bond CH, and double bond CH2, and here we'll have the positive charge. So this is the third structure we have. So these three structures are known as resonating structure. So for this molecule, we have total 3 resonating structure possible. Right? We have total 3 resonating structure possible. So when you compare the stability of this compound, the first one and the second one, right? So since the second one contains more number of resonating structure, we have three resonating structure here, and here we have only two. So we can say the second one is more stable than the first one. Is it clear? It's a pi sigma pi conjugated system. In this, yeah, in this, yeah, you can see. You see here, you'll get the same thing actually. Suppose pi sigma pi conjugation, right? So if this pi bond you shift here, right? So obviously this pi bond has to shift onto this carbon atom. That is obviously true because otherwise this carbon will have five bonds, right? So this pi bond goes here, this pi bond goes here. So here we'll have double bond, here we'll have double bond, and here we'll have the positive charge, which is nothing but this structure. So with this also, you'll get this only. Anyone you can take. Understood? Okay. Now you see the another one. This one you tell me how many resonating structure possible. Possible or not? Yes or no? Tell me. Possible, right? Because again we have pi sigma positive charge or pi sigma pi, right? So when you draw the resonating structure here, so one step first to draw the first resonating structure or one resonating structure, we just shift one pi bond here, right? So here we'll have negative charge. This negative positive forms a bond, and here we'll have the positive charge. So we'll get this double bond here, positive charge here, and this double bond will be as it is. Now in this again two ways possible. Either this pi bond comes here, then we'll get the same structure this, and the second one is what? This pi bond goes here. So we'll get the structure then which is this. Positive charge here, double bond, and positive charge here. Sorry. This is it. Positive charge here we have. So in this you see again there are three resonating structure possible. And if we draw the real hybrid of this molecule, the actual structure will be like this. You see, this is first, second, third, fourth, and fifth carbon. So from fifth to first, the pi electron is delocalizing, right? From here to here, it is moving pi electron, right? So from here, this is 1, 2, 3, 4, and 5. 5 to 1, pi electron is delocalized. So we'll just write down the partial double bond like this. Means pi electron is delocalized from this first carbon to fifth carbon. Now we have positive charge where we are getting positive charge at first carbon, then third carbon and fifth carbon. So we'll have del plus positive charge on the first, del plus on third, and del plus on fifth. This is the actual structure of this molecule. Is it clear? Can you draw the resonating structure of this molecule? First, you check whether resonance is possible or not. If it is possible, then draw the resonating structure and tell me how many resonating structure possible. Tell me. Three. Only three, Advait. All of you are getting four. Is it four? Five. Okay, see. The first structure will draw here. So for that, this pi electron goes here. Here we have the positive charge. So the first structure will be this. Double bond CH2. Positive charge on this carbon atom, and this double bond will be as it is. Okay. Okay, Neha is getting 4. Okay, we'll see. This pi electron again comes here. Double bond we have here. Positive charge, double bond here, and double bond CH2. Again, this pi electron comes over here. Double bond, positive charge, and double bond CH2. And the next structure will be what? This pi electron comes over here. Double bond, and then CH2 plus. So 5 resonating structure possible, 5 RS total, including this. The given molecule is also a resonating structure. You see, in all these, we are considering the given molecule also. Understood? You're talking about carbonate, Bhargava. Shreya, you didn't understand this. Why minus 2 by 3? Okay, see, again I'll explain this quickly. Or I'll go back to the last slide. This one, right? See, you tell me one thing. This molecule has total 2 negative charge, right? Okay, just 1 second. I'll just do it again. This molecule has total 2 negative charge, and this negative charge is delocalizing over oxygen atom. You see here, when this negative charge comes over here, this oxygen will have the negative charge, and when this comes over here, this oxygen will have the negative charge. So in all these three structures, you see this minus 2 charge is moving on to these oxygen atom continuously, one by one, right? So what we can say, that total charge is minus 2, and this is distributed among 3 oxygen atom, right? So each oxygen atom will have charge of what? Minus 2 by 3. It is something like this. If I have 15 rupees, and if I distribute this 15 rupees into 3 people equally, then each one of these will have what? 5, 5 and 5, right? Which is nothing but 15 by 3. So what we are doing here, we have total minus 2 charge, and we have distributed this minus 2 charge onto 3 oxygen atom equally. So each oxygen atom will have then minus 2 by 3 charge. That is what we are doing. Okay. Okay. Now coming back to this, if you have to draw the resonance hybrid of this molecule, resonance hybrid will be what? You see, we have a benzene ring, draw all the sigma bonds and CH2. First of all, you see in this 1, 2, 3, 4, 5, 6. See, this numbering has nothing to do with the nomenclature thing. Okay, I'm just randomly giving these carbon atoms some number. Okay, so don't get confused with the nomenclature part. Okay, so here you see in all these resonating structure, the positive charge present at second carbon, then fourth carbon, and then sixth carbon. Second carbon, fourth carbon, and sixth carbon, and then on the carbon which is outside the ring. Okay, so and this pi electron is delocalizing over the entire molecule. So here you see we have the double bond, partial double bond characteristics among this molecule, which we can show by this circle, partial double bond characteristics, and this carbon also joined by partial double bond characteristics. So this is the dotted line. This has partial positive charge here, and then at the second carbon, partial positive charge, then at the fourth carbon, partial positive charge, sixth carbon, partial positive charge. So this structure is the real structure we have, or we also call it as resonance hybrid. Yeah, no problem, Sriram. Understood. So this is how we draw the resonating structure or various resonating structure possible. Okay. One last example we'll see, and then we'll see the R effect and plus R effect and minus R effect. Okay, one last example we'll see. Two question I'll give you. Tell me how many RS possible for this. We have negative charge here. And the another one is this. Negative charge, double bond and double bond. Tell me how many structure possible resonating structures. Okay, see here this is negative charge, right? So this negative charge comes over here and this pi electron will go onto this carbon atom. So the resonating structure here will be this. We have double bond here and negative charge here. So only two RS possible into this. Because all other carbon you see, these are sp3, sp3, sp3 hybridized. And we know sp3 hybridized carbon does not take part in resonance. Okay, so only two RS possible. In this one, this negative charge comes over here and this pi electron goes onto this carbon atom. So the resonating structure will be like this. Here we have double bond, here we have negative charge, and this double bond will be as it is. Another one you see, this negative charge comes over here, this pi electron goes here, and we have this. Here we have double bond, this double bond will be as it is, and again negative charge will be here. Okay, another resonating structure possible into this, when this negative charge comes over here, this pi electron goes here. So we have double bond here. This double bond will be as it is, and here we have the negative charge. One more resonating structure possible into this. This comes over here, and this pi electron goes here. negative charge, double bond, and double bond. Just a second. Draw it properly. Here we have the double bond. Okay. So now you see, if it is first, second, third, fourth, and fifth carbon, so here the negative charge at first carbon, here the negative charge at first carbon, here we have third carbon, here we have fifth carbon, here we have second carbon, and here we have fourth carbon. So basically in this molecule, the negative charge is present in one by one. It is present at all the carbon atoms, right? So when the charge present at all the atoms in the ring, one by one in the resonating structure, then it means the charge is equally distributed over the entire molecule. Okay, it is equally distributed over the entire molecules or the carbon atom. So if you draw the resonating structure, resonance hybrid of this molecule, the resonance hybrid will be like this. This is the ring, right? And this ring has partial double bond characteristics because it is equally distributed, double bond characteristics, and each of these carbon atom has one negative charge in all this resonating structure, which means the charge is equally distributed over the 5 carbon atoms, and here it will be on each carbon atom it will be minus 1 by 5, here it will be minus 1 by 5, minus 1 by 5, minus 1 by 5, and minus 1 by 5. This is what the real structure we have. Understood this? Why minus 1 by 5? Because we have 5 carbon atom, right? And minus 1 charge is distributed among the 5 carbon atoms equally in all these resonating structures. Is it clear? RS for the previous one, you can draw it easily. You see, 6-membered ring is this. 6-membered ring is this, and this minus 1 charge, we put number over here 1, 2, 3, and 4, right? So minus 1, this minus charge present on first and fourth carbon, right? So you write down here del negative first and fourth del negative. Oh, this is just a mistake. Just it is not double bond. Will not have here. Will have here. I'll just make it correct. Wait. By mistake, I have drawn double bond over there. Let me correct this first. You see this one. What happens in this? This pi electron comes over here on the third carbon, and this negative charge comes over here. So here we'll have the double bond, right? This is a single bond we have. Here we have a double bond. Pi electron comes over here on third carbon. So here we have the negative charge. This is the another resonating structure we have. So the point here is that if you have to draw the resonance hybrid of this one, the negative charge present at first and third carbon. So del negative on first, del negative on second, and pi electron delocalize from first to third carbon, right? From here to here. So we have a partial double bond characteristics like this from first to third. That is it. First to third, we have partial double bond characteristics, and then negative charge, partial negative on this, del negative on first, del negative on third. That is it. Now you understood this first one. Shifting of negative charge connection in the middle. Nothing, you just keep on shifting this negative charge, because you see with practice you will understand that how it is going on. Numbering you do on the carbon atom, you will understand this. Okay, you see if you put the number here, it is 1, 2, 3, 4 and 5, right? So third carbon, here we have first carbon, third carbon. Now again pi sigma negative charge conjugation, so resonance structure possible. So it's here, and it'll have then 1, 2, 3, 4, 5. Just cross checking whether conjugation is there or not. When you get this structure, again you see conjugation is possible. Negative charge sigma and pi. So this will come here, this will go here. You'll get this again 1, 2, 3, 4 and 5. Again you see negative charge sigma and pi conjugation we have. This will come over here, this will go here, you'll get this. Again you see 1, 2, 3, 4 and 5. In this also you see, in this also there is conjugation, pi sigma negative charge. But when this comes here and this goes here, it is nothing but the first structure we have, if you see. That's why further resonating structure is not possible. Did you get this? Yes or no? Okay. Now next one you see, in this resonance we have two types of effect, that is plus R effect, plus R or minus R effect. Like yesterday we have done in the class plus I and minus I. Okay. So plus R, also known as plus M. Minus R can also be written as minus M, where this M means mesomeric effect. Mesomeric effect. So this resonance effect and mesomeric effect are the same thing. Plus M and minus M. Right? Plus R means what? See, first of all, whatever examples we have done, like yesterday class, we have discussed I effect. Okay, not for Rajinagar. I will discuss this I effect in Rajinagar also later on. But I effect I have discussed yesterday, and there, if you remember, I told you that there's only sigma electrons involved, right? But the difference in R effect is what, or mesomeric effect is what? Here we have pi electrons involved. That's why you see always pi electrons shift from one point to another point, or one carbon to another carbon. So here we have pi bond, pi electrons involve, and there we have sigma electrons involved. That's the difference we have in these two, right? That one is distance dependent, this one is not distance dependent. Okay. So here you see, if I write down what is plus R effect, plus R group, plus R or plus M are the same thing. Plus R group are electrons releasing group, like we have plus I, and minus R or minus M group are electrons withdrawing group. Withdrawing group. Okay, that withdraws electron from the ring. Now you see here, if I write down two examples, how do you know that the group attached to the ring is electron withdrawing or electron releasing? That's the thing. Suppose we have this OH, and the second one, if I write down C double bond O and OH, right? So how do you understand that the group attached to the ring it is electron releasing or electron withdrawing? Okay, so only two things you have to keep in mind. Okay, if the group attached to the ring contains any negative charge or lone pair, then it is electron releasing. Okay, if the group attached to the ring contains any negative charge or lone pair of electron, then it is electron releasing. Now here you see when OH is attached with the ring, so it has two lone pair, so it can donate this lone pair to this carbon atom, and this pi electron comes over here. This is nothing but resonance now. Okay, so the resonating structure we draw here will be like this. Oxygen attached with double bond now, because this bond lone pair comes into bond pair OH. Now when this oxygen loses its electron into the bond pair, so it will have positive charge onto it. And now this pi electron comes over here, so on this carbon will have negative charge, and then all other bonds will be as it is. This is one resonating structure. Another resonating structure we can draw when this negative charge comes over here and this pi electron goes here, because this is a conjugated system. So we'll get this double bond OH, positive charge on oxygen, double bond we have here, double bond we'll have here, and here we have the negative charge. In this again, this negative charge comes over here, double bond goes here, and this will be double bond negative charge, double bond OH plus. And the last structure will be when this negative charge comes over here, this pi electron goes here, and we get this double bond, double bond, double bond, and OH. Is it clear? Tell me fast. So this group you see, OH is electron releasing. That's why it is plus R group, OH. All those groups which has lone pair or negative charge present on the atom with which it is attached to the ring is known as electron releasing group or plus R group. Understood this? You write down this point somewhere. If the group attached to the ring contains lone pair or negative charge on it, then it behaves as electron releasing group. Okay, electron releasing group. So this is how you can understand, okay, if lone pair or negative charge present. Now coming back to this example. So this is the example of plus R effect. Now in this example, you see this carbon does not have any lone pair on it. Okay, so when the group attached to the ring or the atom with which the group attached to the ring, that atom and any other atom, if it contains any unsaturation or double or triple bond, then the group behaves as electron withdrawing group, and this is minus R effect. Now, how it is electron withdrawing? You see, this has a double bond between first and second atom, has double bond. So this pi electron goes here because it is pi sigma pi conjugation. Again, pi sigma pi conjugation. This pi electron goes here when this pi electron jumps onto this carbon atom. So the another resonating structure you'll draw, that will be double bond C O minus and OH. And here we have the positive charge because the pi electron goes onto this carbon atom. Then double bond and double bond. Another structure is what? When this pi electron comes over here, so we'll get double bond here. All other thing will be as it is. O minus OH, double bond here. Here we'll have the positive charge. Another one you see, when this pi electron comes over here, double bond, positive charge here, double bond C O minus OH. Now, the last thing is what? When this negative charge comes over here, this pi electron goes here, and we get double bond, double bond, double bond, C double bond O, OH. So this is the resonating structure again we have due to minus R effect, electron withdrawing nature. Is it clear? Yes, can we move ahead? Tell me. Okay, so this is like for you to understand. We'll discuss some more example of this into the class, right? We'll move again, we'll move ahead in hyperconjugation and all. So this is actually the plus R and minus R effect. Okay, we'll do some more example, some more example, good examples on this into the in the class. Right now we are moving ahead into hyperconjugation. Next, write down the another electronic effects we have, that is hyperconjugation. Write down into this. It takes place, hyperconjugation takes place. What is hyperconjugation? I'll tell you. It takes place only in the case of carbocation, alkene means double bond if it is there, or free radical. For Rajinagar student, you must have you must get confused with this. What is free radical and all. So don't get confused with all this. Just you write it down. When I'll discuss this in the class, you will understand this. Okay. This is not important now. I'm just giving you the information here. Okay. So carbocation, alkene, and free radical. Next line, write down carbon ion does not take part. Carbon ion does not take part in hyperconjugation. What is hyperconjugation? I'll tell you again. First, you write down these information. What is the condition for hyperconjugation we have? That you write down. Condition, you write down condition for hyperconjugation. Write down sp3 hybridized carbon, sp3 hybridized carbon with at least one hydrogen, with at least one hydrogen must be connected with a positive charge carbon or double bonded carbon or free radical, right? Or free radical. Now you see what hyperconjugation is. Suppose if I write down this example, carbon has 3 hydrogen here, and this is connected with carbocation, CS2 positive charge. Condition you must read. It is given that sp3 hybridized carbon with at least one hydrogen must be connected with positive charge carbon, double bond or free radical, right? So you see this one, this is positive charge carbon. This carbon is sp3 hybridized, right, which has 3 hydrogen. The condition is at least one hydrogen it should have, right? This is alpha carbon also. So in the condition you can also write it down sp3 hybridized alpha carbon. That would be better. Hybridized alpha carbon. So this is carbocation and this position is the alpha position. This is alpha carbocation. So when sp3 hybridized alpha carbon contain at least one hydrogen atom, then hyperconjugation is possible. First thing is this, right? When sp3 hybridized alpha carbon contains at least one hydrogen, then hyperconjugation is possible. Now, what is hyperconjugation? You see this bond pair here. Because of this bond, we have a bond pair here. So what happens? Because of this positive charge present here, this electron pair is dragged by this carbon atom towards its side. And the structure that you get here, we call it as hyperconjugative structure. And that structure will be HC. Here we have H plus because the bond pair of electron which has one electron of hydrogen also comes over here. Double bond CH2 and this hydrogen will be as it is. Right? Now, this in this it is also possible that either this bond pair comes over here or this one comes over here or this one comes over here. Any one of these bond pair can come, right? So in all these possibilities, the possible hyperconjugative structure will be this. And the last one will be this. CH2. This structure will get when this bond pair comes over here. This structure will get when this bond pair comes over here, right? So these are the hyperconjugative structure. Now the point here you have to note is what? Write down this H plus ion, H plus ion without any bond, without any bond present over there, present over there. Hence, we also called hyperconjugation as no bond resonance, as no bond resonance. See, this bond pair comes over here, but H plus is not going anywhere. It is there only within the molecule. Actually, in this, what happens? This bond breaking and bond making takes place simultaneously. Sometimes this comes over here, this bond break, and then this comes over here, this bond will be as it is. This comes over here, this bond will be as it is. So any of these structures are possible, or these structures are interconvertible into each other, and this we call it as hyperconjugative structure. Okay, now if you have to find out for a given molecule number of hyperconjugative structure, number of hyperconjugating structure, for this what we write for this one, you see, for this one you see the total hyperconjugating structure will be 1, 2, 3 and 4. These three structures you see, it is because of these three hydrogen atom, which is the number of alpha hydrogen atom. So number of hyperconjugating structure formula you can write number of alpha hydrogen plus 1. Okay, number of alpha hydrogen plus 1. Is it clear? Number of hyperconjugating structure is equals to number of alpha hydrogen plus 1, the formula we have. One more point you write down here. More hyperconjugating structure, more hyperconjugating structure, more will be the stability, and more hyperconjugating structure means what? More alpha hydrogen. So to sum up all this, if number of alpha hydrogen is more, then more will be the stability of the compound. Okay, like you see, on the basis of this, if I give you one question, you have to compare the stability of these molecules, stability order. C carbon positive CH3, CH3 and CH3. This is 3-degree carbocation. Then we have CH positive, CH3, CH positive CH3, CH3, CH2 positive, and then we have CH3 positive methyl. Okay. In these four structure, if you compare the stability, how many alpha hydrogen are present here? Alpha hydrogen are those hydrogen which is attached with the alpha carbon, right? Alpha carbon is the carbon which is adjacent to the functional group or any carbocation, carbanion, whatever it is. So you see these three are alpha carbon we have. So total number of alpha hydrogen is 3 plus 3 plus 3, that is 9. Similarly here the alpha hydrogen is 6, alpha hydrogen is 3, and there is no alpha hydrogen, right? So more number of alpha hydrogen, more will be the hyperconjugating structure and more will be the stability. So stability order is maximum for this, then we have this, and then is it clear? Okay. So this is what hyperconjugation is. The last part we'll discuss now, and that is electromeric effect. Electromeric effect is the only temporary effect. The only temporary effect. Now, in this one, you see, this effect involves this effect involves complete transfer of shared pair of electron to one of the atoms joined by a multiple bond. At Okay, the effect involves the complete transfer of shared pair of electrons to one of the atoms joined by a multiple bond under the under the influence of any attacking reagent. Okay, so this kind of shifting of or transfer of electron takes place under the influence of attacking reagent. Okay, next line you write down, as soon as attacking reagent removed, the original condition is restored. Means whatever the molecule was initially will get the same molecule, is restored. That's why it is temporary effect. Okay, that's why it is temporary effect. This kind of effect only observes in the molecule contains multiple bond. In the molecule contains multiple bond, either double or triple, multiple bonds there. Okay. Now in this one, if I take the example here, suppose the compound is this C double bond O, right? So in this case, what happens, since oxygen is more electronegative, so obviously any nucleophile, if it attacks, this pi electron will shift towards the more electronegative element, which is nothing but oxygen. So we get here C positive and O negative charge on it, right? This is how shifting takes place. Now this I'll give you some example here. But before that, we'll see the types of electromeric effect. This electromeric effect are also two types of electromeric effects we have. The first one we'll write plus E effect. Plus E effect you write down when transfer of electron takes place towards the attacking reagent. When the transfer of electron takes place towards the attacking reagent. Meaning of this is what? Suppose we have carbon-carbon double bond, right? And suppose H plus is attacking onto this carbon atom. So suppose if this bond shift over here, right? And this H plus attached onto this carbon atom only. Means the attachment or these H plus will attack onto the carbon atom where the bond pair of electron is shifting. So this kind of attack or reaction, it comes under electro plus E effect or positive electromeric effect. The product that you get here will be this carbon will have positive charge because the bond pair shifted towards this, and this carbon will have one hydrogen with two bond as it is, right? So this kind of effect is electromeric effect when the bond pair of electron shifted towards the carbon atom where the attacking reagent where the attack is taking place, right? So this is plus E effect. Now the next one is negative electromeric effect, which we also call it as minus E effect. Negative electromeric effect. When this is possible, when the transfer of electron takes place away from the attacking reagent. For example, you see, if I take this C double bond O carbonyl group and the nucleophile is Cn minus, this Cn minus is attacking onto this group, right? So obviously, since oxygen is more electronegative, this bond pair will shift toward this, and since this is negatively charged, so this will attack onto the positive side. Oxygen will take the bond pair of electron, so this will never attack onto the oxygen, but this will attack onto the positive side. So you see, this attack takes place away from the shifting of electrons. The product here would be C with this cyanide group and O minus. Right? Simply one thing you can keep in mind here, that attacking reagent will not attach where on the atom on which the electron is transferred, right? That's the meaning simply we have in minus E effect. Now, when I say this temporary effect, why it is temporary? Now you remove this cyanide group from here, again you will get C double bond O, the same thing. That's why it is temporary effect. In previous example also, you remove H plus, again you will get C double bond C over there, right? So that is what we have, the temporary nature of this effect. Okay, you remove attacking reagent, you'll get the original compound as it is. Is it clear? Okay, so the last thing we'll discuss today is carbenes. Okay, see, I'm just discussing the basics of all these concepts. Okay, application part again we'll see. Okay, we are not completing the portion here, right? And for Rajasthan Nagar students, if you are getting 50% of this also, this helps you a lot when I discuss these things into the class. Okay, so next to write down the one intermediate we have, and that we call it as carbene. The last thing for today, just I'll take 5-10 minutes more. Carbenes. See, like carbocation, carbanion, free radical, carbenes are also the intermediates, one of the intermediates we have. And similarly, we have nitrines also. Okay, so that also we'll discuss nitrines. Okay, carbene is nothing but methylene group. Carbene is methylene only, which is nothing but CH2 with one lone pair. Methylene is CH2, one lone pair. Okay, write down into this. These are the neutral covalent compounds neutral covalent compound of carbon having two bond pair and one lone pair. You see, two hydrogen, two bond pair and one lone pair. Okay, one lone pair of electrons. So if I write down this one, C6H5 CH, one lone pair on it. Again, you see, this is what one hydrogen from here has been replaced by this phenyl group. So we call it as phenyl carbene. The name of this is phenyl carbene. If I write down any alkyl group here, RCR, one lone pair on it, this is dialkyl carbene because the hydrogen is replaced by two alkyl group. Dialkyl carbene. Now, this carbene exists in two types. Carbene exists in two types. Two types of carbenes are there. The first one you write down, singlet carbene or only singlet. Singlet. In this type, write down in this type, in this type, both unpaired electrons both unpaired electrons go into the both unpaired electrons goes into one orbital and have opposite spin. First you write down this, I'll explain what is this, what this means. Opposite spin, and it forms bent structure. Bent structure. You see this one, singlet carbene is this C with two hydrogen, and the two electron that you have, unbonded electron, is present in one orbital, one p orbital. One is up spin and down spin. They are like this. Clockwise, one electron is clockwise, other one is anti-clockwise. Okay. Now you see here there are few properties of this. It is less stable. Less stable means in comparison to the other carbene that we'll see in some time. It is less stable since both electrons are paired now, so it is diamagnetic. And we also call it as hot methylene, just a name. Hot methylene. Okay. Now, if you calculate the spin multiplicity of it, spin multiplicity, the formula is 2 summation s plus 1. Now, how do we calculate this? 2 open bracket, one electron is clockwise, other one is anti-clockwise. For clockwise plus half plus one electron anti-clockwise, and for that it is minus half, bracket close plus 1. This is nothing but the s, summation of s. So this will get cancelled and will get 1. Now you see, since this spin multiplicity is 1, that's why we are calling it as singlet carbene, because of spin multiplicity, right? How do we calculate this? Formula of spin multiplicity is 2 summation of s plus 1. S, how do we calculate? 1 electron clockwise, so 1 into plus half for that, plus 1 electron anti-clockwise, 1 into minus half for that. So plus half minus half gets cancelled, we are left with 1. So spin multiplicity is 1, that's why it is singlet carbene. Now we'll do the last thing in this, which is triplet. When we calculate the spin multiplicity of this, we'll get 3. We'll do that. Okay. First, write down in this type the electron goes into different orbital with same spin. It has linear structure, sp hybridized. sp hybridized. This one is sp2 hybridized. Here, write down, it is sp2 hybridized. Okay, so the last thing you see, if I draw the structure of this, we have H, C, H, and the 2 electron will be in 2 different orbital with one electron each of same spin. Okay, now the two things here, since the electrons are unpaired now, so it is what? It is paramagnetic in nature. The previous one was diamagnetic. It is paramagnetic, right? The name of this is called methylene, just opposite of that, and it is more stable than the singlet one, since the 2 electron is in different orbital, less repulsion will be here. Okay, when you calculate the spin multiplicity of this, the formula is again same, 2 summation of s plus 1. But here what happens, both electron has clockwise, right? So 2 into plus half, I have written it together only, or we can also write 1 into plus half, then again 1 into plus half, plus 1. So when you solve this, the spin multiplicity you'll get as 3. Okay, and since this is 3, that's why we are calling it as triplet. The name of this is triplet. So this is it for this carbene. We have two types of carbene, singlet and triplet. Okay, so today I have given you the basic information of basic concepts of GOC. Okay, application part, we'll discuss this in class again. Few things are left in application part, but the theory, the basic thing, definition we have covered with few examples. Okay, so I hope you have understood this. Okay, next class, whenever we have, we'll continue some application part of it, and then we'll see some more examples. Okay, thank you. Any doubt you have, you can ask me.